So today I have an obscene amount of slides. I have 59 of them. And usually it takes about 16 slides per 45 minutes, so that's not going to add up. So I am going to crank up the speed, maybe, hopefully, I don't know, but that kind of depends on you also making sure that you stop me when something doesn't add up. Because otherwise I am just talking to nobody, and that's I mean, I can do that, but it's not super productive. So be sure to stop me if you have questions, because a lot of content, short amount of time, kind of cramped, but hopefully we can kind of catch up. You're all now roughly in like exercise 4 territory, maybe gotten a bit further than that, and that part is, well, now we're getting into the actual programming part. The goal was to get you all prepared for everything that you need to actually start programming before you started programming, so this is kind of, we're talking about things that, well, we're talking really about module design today. And while we, from experience on the presentations, we realized that absolutely none of you had any decent module diagrams, which makes sense. You haven't started programming. Like you don't see what you really need to do, to make and how to structure it before you start making it, which is one of the reasons that we don't really say that you, like the kind of the V model way of thinking, where you design everything first and then you implement it and then you test that and make sure that your design was correct. It doesn't work because you don't know what you're making before you start making it, and you don't know what's possible to make before you started trying to make it. But so today is, again, as before, first principles thinking. But today also, unfortunately, there is a bit of an angle into the code quality perspective. And so there will be some claims, some perspectives, some ideas that are angled not from strictly first principles, but more from like, I don't know, zeroth principles. More like, what do we think is good and why do we think that, why do we think those things are good and why do we like them? And I'm not necessarily going to justify all of them. I will later. But for now, we're just taking them on the intuition that things that are nice are good. But I'm not going to justify it any further than that. So, well, first, let's go through where we are, just so we kind of get the lay of the land, see where this fits in with the previous contents in the course, and also, I guess, future content. So we've been through. Well, we're making robust software, and robustness, the only way to get robustness is if it fails, it can't fail. So we need to do it again. And we have 2 solutions to doing it again. And I saw some confusion about this, so let's just get this one straight. There are 2 options. One is to do it over, which is the designing for crashability perspective. So we can either do everything over, or we can do only some things over. And the restore points are optional, and the undos are optional. Right. So if a single node crashes, completely loses power, you can't do it over because it's crashed, it's dead. So then we need to go into option 2, which is do it somewhere else. And this is the distributed systems part. So these 2 are combined. These provide the vast majority of our robustness, assuming that we already have a program that works. If it's designed in such a way, it gives us a lot of robustness. The problem with distributed systems was that there is no general solution. So you can't just import distributed systems.h and it works. You need an application-specific way of thinking about it. And in our applications, typically of the 3 of consistency, availability, and partition tolerance, we need availability and partition tolerance, right? So we need it to actually do something all the time, and we need it to do something even if it is disconnected. So that leaves us with consistency, and having a program that doesn't have consistency is going to produce random outputs. We don't like random outputs, so we want some amount of consistency. How do we deal with this? Right, so the way we did this was by finding what was permissible in the land of inconsistency, and the only way we can find this is from the specification, hence the no general solution part. And the way we did this, and I mentioned briefly last time that the way we did this is with state machines. All right, so we formulate, like we can get random messages from the network. We don't really know what we're going to get. That's the point. The messages need to be unpredictable, otherwise why send a message? And so the messages can either be kind of going forwards, they give us new information, or they can be going backwards and they give us old information. And the way we do this, handle this, is by we formulate the rejection of negation, like we reject going backwards. So we have a double negative here, and the double negative forces us to go forwards. And I said the way we formulate this is with state machines. And I realized I encountered some second-year students taking cybernetics, and apparently in the previous course, which is like the course content isn't the course isn't a prerequisite, but the content is, and I thought one of the content prerequisites that was satisfied by that course was an understanding of state machines. And it appears that they are not actually forced into understanding state machines by implementing the previous elevator project as a state machine. They just, most of them hopefully end up there. And so I need to explain state machines in more detail, and I will anyway, but I will explain it from a code quality perspective. Why do we design it this way? Why is this a preferred solution? But that was not actually done previously. So when I said, do a state machine, it appears that not everybody necessarily knows exactly what I'm talking about when I say that. Unfortunate, but reality. I'm not fully healed. On the processes side, we have talked about this several times, that our system is composed of several tasks. We have talked about that the tasks do something, they produce some output. We have said that they are mostly independent, and the dependencies are messaging. So we're making lots of tasks, and they send messages between them. We haven't really justified this design yet. Right? We've just briefly encountered it as a result of the first exercise, where pretty much everybody said that doing it the message passing way was more intuitive. And the reason why it was more intuitive, because it was clearer, the semantics around ownership and the semantics around responsibility. Now, responsibility aren't technically semantics. They're more like, I understand one piece of code at a time, and that makes it easier to understand the program. But we haven't justified it beyond that. It's just purely intuition so far. We talked about inputs needing to have, no, not inputs, tasks needing to have input, output, and states in order to be useful. If they don't have all three of them, they're not really a task, they're just a function or some data. So processes are only useful if they're stateful, and messages are only useful if they're unpredictable. We have only justified this in terms of distributed systems. Right? So we're only justified this when it comes to sending messages across nodes, between nodes. Right? So there's no point in sending a message to another node if you're literally always sending the same thing. That's kind of not useful. And having a different node, if it always does exactly the same thing, and it doesn't, then you don't need to communicate with it. It's always going to do the same thing. So we've only justified it in that perspective. We haven't justified it in terms of distributing, in quotes, our program into multiple tasks on a single node. So we haven't really justified multi-threading in the same way. So that is the goal for today. So the goal is 2 parts, and hence that's why we have 59 slides. How to structure the content of a single process. So we're going to cover the state machines part there. And then also a single process, well, there's a lot to do sometimes. And in order to do that, we need to do it in a structured way. So usually the way we think about it is, okay, we have algorithms, we have data structures, we have functions, we have classes, we have whatever. And the question is, when do we divide things into those components? And what kinds of components do we want to divide it into? So that's not module design, but internal for one module. How do we structure the code in such a way that it is good code, whatever good code means? And then on the larger perspective, how do we structure a single program into lots of subtasks? And how do we, like or if you have a problem, a large problem, how do we divide that problem into smaller problems? And what constitutes one problem not being the other problem? So this is the core of module design, like what goes in this task and what goes in that task, and what is the boundary between them? How do we define this? And in order to talk about this, I need to cover a little bit about object-oriented programming, which you are mostly all familiar with. Yes? Give me a hand for object-oriented programming being briefly familiar. Give me a hand for like design patterns, like Gang of 4 design patterns. Encountered that? Okay, good. So you haven't been completely destroyed mentally yet. So that's good. No, because when you have design patterns, that's an indication that the tool you're using isn't good enough, right? Because if the tool you were using was good enough, there wouldn't be any design patterns. You would just use the tool and you wouldn't need to think about like, oh, we need to use the tool in this way. There's only one way to use the tool, and it's the correct way to use the tool. So design patterns are an indication that you've fucked up somewhere along the way. Though speaking of which, the first thing I'm going to talk about today are state machines, which is a design pattern, which indicates that C is not the best, well, imperative programming in its strictest form, like a C-like program, isn't the ideal way to make a process-oriented program, which makes sense. But a more, a Go, on the other hand, does have a lot of nice tools to do this, but it also has a larger toolkit. There's nothing stopping you from making bad code in any language, really. So, well, that's that. But first, the first design pattern, state machines. So let's just set up some goals. Like, what do we want to make? Why? Okay, just goals. Goals. What do we want? Okay, here's the idea. We want to make a pattern, a kind of structure in our code, or a structure that repeats, so that when we see it, we go, aha, I understand what this is. Briefly, I just need to understand the details. So we want to make a pattern that has a loop, because our program needs to run forever, so that one should be pretty easy. It reacts conditionally to inputs, so it doesn't always do the same thing when it gets the same input. It actually behaves differently at different times. And the only way to do this is that it reacts based on the history of previous inputs. Nah, fuck it, no examples here. It can accept inputs in any order. That's a good thing to have, because if you can't accept inputs in any order, then the behavior of your thing is dependent on the one using your thing, not you. So you want your behavior to be dependent on you, not whoever is using you. And we also want to make sure that the behavior is correct regardless of the order. So we want to make this easy to verify. How would we do this? Well, it needs to be code that we can understand in some capacity, because we can't be sure that it's correct unless we understand it. And we also want to make invalid data combinations inexpressible, right? Because if we have a large array of, well, not literally an array, but lots of Booleans in our structure, we have probably a bad time, because there may be some combinations of those Booleans that don't make sense. And so we want to reduce that as much as possible in some way. Because if we have the combination of data that is invalid, having it expressible in our code means that it will end up in our code, which means that the bug associated with an invalid piece of data will show up in our code, which is a bad time. So it's just to make wrong data kind of bugs impossible. And finally, we do want an intuitive if this, then that kind of structure. I think most people here understand if statements, right? It's not the hardest thing in the world. There are more complicated control flow structures than this, but an if statement is, everybody kind of gets this. So that's good. So these seem like reasonable goals. Anything that somebody is like, yeah, no, having this as a goal is going to end up in hell. No, these seem like good things. Okay. These aren't justified in any large, well, they are partially justified, but fundamentally these are based on intuition so far. So if they match your intuition, that's good. If they don't, please tell me, because otherwise then we need to work on that. No? Seems reasonable? Okay. So let's just get to work. Step 0, create a loop, creating an outer loop. Our program needs to run forever. This is really easy, so I'm not going to talk about it, because you all understand an infinite for loop, hopefully. So let's get to the interesting parts. We need to find the inputs and outputs of our process, because our program needs to depend on the outside world, and it needs to affect the outside world. If it doesn't do that, then it's not really a program now, is it? Now, we do want these to be formulated as discrete time, so think events instead of the state of something. And I am going to justify this here. Why do we want events instead of the current value? The first one is for debugging. The less CPU usage thing is not super relevant, but because, well, we have plenty of CPU. It's not, well, maybe you don't, but usually you do. But the less spam, it's easier to log things, it's easier to see what happens if it only happens once. If the same thing is happening all the time and you're trying to print it to the screen, yeah, good luck with that. So that's not going to work. If you do need to save something, if you need the current value, you can just take the event and be like, oh, that happened, so therefore the current value is whatever happened the last time. So you can save your own current value if you need to. So you don't need to look up the current value somewhere else, you can just save it for yourself. So if you get events in, you can create a current value from it, but if you have a current value, creating an event from it is a bit harder. So once you have the event, keep it that way. And if you need like a continuous output, you can generate that with a timer. So the timer ticks periodically, and then you produce your periodic output. So a continuous output can be produced from events in that way, and you also get like perfect timing for it as well. So events are just easier to work with. Make sense? Yeah. So examples. Ooh, finally. So for the elevator, I'm not going to go through the whole thing. I'm just going to go through the one that is on the project resources repository, which has just the button press, floor sensor arrival, and the time as inputs. And for the outputs, motor direction, door, floor indicator, and button lights. It doesn't have the obstruction switch, and it doesn't have the stop button, but the stop button isn't part of the specification for you guys anyway. But let's use our imagination for it and just keep it in the back of our head. What would happen if the stop button existed here? There aren't any more than this. So we need to connect the inputs to the outputs, and we need to make this behave like an elevator. And that's not necessarily super intuitive how exactly to do that. So the first thing we realize is that we can't just set the motor direction based on the button presses and the floor sensor arrival. Right, we also need to know where we are and what direction we're going and so on. So when somebody pushes the button, it doesn't suddenly change the direction of the elevator whilst it's moving. So there is some data that we need as well here. There is some persistence we need. So that would be step 2, getting the persistent data in here. So we need to store what inputs have happened, and we need to store what outputs we set so that we can recall them in case we need to recall them. So, well, we want conditional behavior, right? And in order to have conditional behavior, we need to have something to put inside the if statement. And that something needs to be data. So that data needs to come from somewhere, so we need to store it. It's not a more complicated argument than that. And then we put the goal, the constraint on that, which is that the stored data should be minimal. So we don't want to store more data than necessary, because then we can get invalid combinations. Invalid combinations lead to bugs. Bugs leads to sadness. So duplicates are out, invalid combinations are out. And there are some methods to do this. You can do this completely analytically. You can just like, okay, these are all of the inputs, put them in rows. These are all of the outputs, put them in rows. And then you go through every single combination of all of them, and you go, okay, which ones are invalid, which ones are duplicated, and you remove them. So I'm sure you've done this in some kind of digital electronics design course of some kind. You've probably seen implication charts and row matching and all of that good stuff. These are analytical methods that exist to kind of reduce the state space of a state machine. I'm going to get back to why I think these are a bad idea. They're a good idea, but they're also a bad idea. So the more intuitive way is kind of start with as little as possible, and you go, okay, well, we need to save this because reasons, and then you add those incrementally. The problem with that is that you may add things that you don't actually need to add, and then you need to realize that there is room for reducing, and then you need to start analyzing and thinking. So the smart thing to do is to use a bit of both. Right, the specification is written by a human for a human, so we need to use a human to understand it. We can't just use the analytical tools, which is why the analytical tool doesn't actually work, because you need a human. And humans are pretty, well, they're good at analysis, but the tools we make for analysis aren't good enough that they can be used without a human. So for stored inputs, what are our things that we could store? These are the things. What buttons have been pressed, what floor we were on previously, if we are between a floor or at a floor, and what floor we're at if we are at a floor. The 3-second timer for the door, like when it started or when it will expire. Stored outputs, if we are moving, what direction we're moving, if the door is open, what button lights are. So some of these are Booleans, some of these are tables. So the goal here is to minimize them. Can we get rid of these Booleans and condense them down? Are there some of these tables that we don't actually need? Or is there some content that we don't actually need? So on the minimizing step, we can do this entirely analytically, as I mentioned. It's really inefficient because you get a really, really large state of spaces, so trying to think about it becomes really hard. So instead, here's just a list of intuitions. So some things don't need storage, right? The call button lights in this simple elevator example. For yours, it's going to be a bit harder. But for the simple elevator, you don't need to store what lights you've set. You just need to store what buttons have been pressed because there's direct one-to-one mapping between them. So one of them just goes straight out. You don't need both of them. There are some things that are integer-like or Cartesian-like. You understand Cartesian products, right? So you have one dimension and then you have another dimension, right? So we have direction, up, down, and stop, and then we have another dimension, which is what floor we're at. So we can be up at one floor or up at another floor, or down at the first floor or down at the second floor. So it gives us a multi-dimensional space. So floor number and direction are the two big ones here, right? So the elevator behavior is the same regardless of what floor we're at. It is also the same regardless of direction we're in, because upwards is just downwards, backwards. And then there are big things. If you have a large table, like the table of orders, setting that up as like a large list, up, down, up, down, up, down, up, down, Boolean, pressed or not pressed, and then we put that in our giant implication chart, it's going to get really large. And so the things that are interesting here isn't each individual table or each individual element of that table. The interesting part is things like, are there any orders? Are there any above us or any below us or any at this floor or any in this direction? And so it makes sense intuitively to kind of disregard them. And then we have like one-shot things like the door close timer. Like there is no state there, it's purely transitional. So these, you already have these intuitions when you're designing your own state machines. You go, yeah, that makes sense. You're not actually thinking about this in this way. The things just kind of click on their own. But the point is that when you are making a state machine you have lots of inputs, lots of outputs, you could program this as literally a giant lookup table. You could program the elevator code for this as was it going to be like 120 something by whatever lookup table. And then you just go, oh, this is the matching column for our inputs, and this is the event that happens. Look it up, produce an entire column of outputs, and then recurse that back onto our inputs. You could do that. But from a code quality perspective, trying to understand, is this table correct? Good luck. It's not possible. So you need to make a tool to generate that table, and then you're back here. So for the elevator, the things that are kind of cut out now, well, we've cut out a lot of things. So the things that remain are really these three Booleans, right? If we are at a floor, if we are moving, and if the door is open. So these are 8 possible combinations here. And now we can start thinking, okay, can we use the good old-fashioned analytical method for this? So we have some invalid combinations. This is a table of invalid combinations. If we are moving with the door open, from the specification we go like, this is technically possible behavior, but we don't want that to happen. So since we don't want it to happen, we go, let's just make that combination literally inexpressible in our code. Let's just get rid of that. Yeah, if the door is open between floors, that's also technically, it works. It's a thing we can do. It's a bad idea, but we can do it. And also stopping between floors. Again, it's something that we can do, but it's a bad idea. So if you just draw up all these 16 possible combinations, no, sorry, not 16, these 8 possible combinations, and you just remove all the rows that match one of these 3, you're going to end up with these 4 combinations that are the remaining ones. So these are the only remaining ones, right? We're moving between floors, idle, door open, moving, passing floor. These are just, you find what combinations are and you go, okay, what does this look like? And you give it a name. And these are the 4 ones that remain. And this is why we get these states for the state machine. Very quickly gone through all of this, but this is where the states come from. They're not pulled out of thin air, they're actually analytically derived in this way. Now you may notice that we have 2 moving states. So there are some things to notice here. The analytical method on its own isn't actually analytical. That's the thing. Finding what combinations are invalid is something a human has to do. Giving them names afterwards is something a human has to do. So it's not actually an analytical method. And also, when we found the minimal states, we had 4 of them, but we have 2 moving states, and they're actually equivalent because we have a don't care there. So it doesn't actually minimize the states, but it gets us in the right direction. And it's also not obviously extensible. So what do we do if we were to add the obstruction switch to this, or what would we do if we were to add the stop button to this? So if you were just kind of designing incrementally and go, oh, we need this extra feature as well. How would you do this? So the question is, do you need to start completely over if you were to add either the obstruction switch or the stop button here? And that's a hard question to answer, because in this case, for the obstruction switch, no, you don't have to start over, but for the stop button, if you had like an emergency stop button functionality, like hard stop the elevator between floors and let people off if it's at a floor. For example, if that was a specification for the stop button. If that was the case, then you would have to start over. But for the obstruction switch, if it's just like, make sure the door doesn't close while there is an obstruction in the door, do you need to add an extra state for this? No, not really. And the question is, why is that the case? And is there any way to know which one of these will be the case before you start? And the answer to that is no, there's no way to actually know this. There's no analytical tool that can tell you, okay, we added something, added a new feature, do we need to redesign our state machine from scratch? You just need to start from scratch and be like, okay, did we end up with the same thing or not? So you don't have to start over with the obstruction switch, but the only way to find out is by starting over. So there is some sadness here, unfortunately. And I can't explain that intuition. I haven't gotten that far in my own thinking. But if you see that intuition, good for you. Please tell me about it. But I don't see it yet. So step 4. We've minimized our states. We figured out we've put up a loop. We figured out the inputs, figured out the outputs, figured out the data, and minimized the data. So now we need to conditionally react to these inputs given our data. So we have a set of event-like inputs. We have a set of technically event-like outputs. We have an enumeration of the unique states. And I put states in quotation mark here because state can mean like the current value of some amount of data, or it could mean like the finite state machine state. And now that term is overloaded and we have some issues there. So that's going to be a problem. And then we have some additional data that was inconvenient to add to that enumeration. So in this case, it would be floor, direction, the table of orders. And anything more? No, nothing more. So we have 4 things here, and there is some function that maps between them. So we have the inputs, the state, and the data at some time t, and from those 3 things, you generate the outputs and the next version of the state and data. The problem is that this function is pretty fucking big, so we need to split this into smaller blocks. And the question is, what are those smaller blocks? How do we split this giant function into lots of smaller functions? And how do we make it look good in code? And how do we make sure that we understand it? And all of that good stuff. And what does good code mean? But we'll get to that one. So there are two natural levels of splitting here, because we have the inputs, which are events, and we have the finite state machine state, which is also a discrete thing. So we have the input event and we have the current state. Those are two natural, they are small in number. You have a limited number of inputs that could happen, and you have a limited number of state machine states. That was the point. That was the reason why we were limiting them, was to make this small. So we have two natural splits there, and the question is, which one do we split on first? Do we check the input first and then check the state, or do we check the state first and then the input? Both of these are possible in code. There's nothing stopping you from doing one or the other. And we need to develop some amount of intuition for what is the best approach here. Should you lean in one direction? Should you lean in the other direction? Should you always do one of those two, or should you kind of try both and see which one fits best? One suggestion is like whichever gives the least amount of code duplication. If you need to do the same thing in every one of them for some of them, then maybe it makes sense to kind of flip it on its side and you remove some of the duplication, and that makes it more readable. That could be one indication. So here's a heuristic or an intuition. Again, there's no like hard, fast rules here. You can program whatever you want. Nobody's going to stop you other than yourself when you go, I have made a mistake. So there are some inputs that have mostly the same action no matter the current state. For the elevator, for example, the button press satisfies this, right? So we're going to add the button press to the order table no matter if we're moving or if we're idle or if the door is open. We always need to store it. So because of that, it makes sense to kind of switch on the input first, because no matter what the input was button press, and no matter what state, do the same thing. So we can kind of move it before we check the state. And then there are also some inputs that are only acceptable in particular states. And so maybe that doesn't actually make sense. Maybe this argument doesn't make sense. I might have fucked up here. Because there is like only a single input and then a single state that makes sense to do it. Oh yeah, here's why. For example, the door close timer. If you check the door close timer and then check, are we in the door open state? Yeah, that makes sense. That's the only time it makes sense. And if you are in another state, you can just ignore it. So you can just go, oh, we try to close the door when we're moving between floors, doesn't make sense, don't care, ignore. But if you were to do it the other way around, and you're like, oh, we're in the moving state, so we need to check all of the inputs that can occur. You still need to check for the door close timeout, because if you don't check for it, you have a message that's filling up your inbox that's just hanging there and doing nothing. And at least if you're doing it in the message passing way, you're gonna need to check it just to clear it out. So it's more of like a code functionality thing more than anything else. There are some cases where it makes sense to kind of keep a message for a later state and just put it at the back of the queue. But kind of reordering or re-queuing a message like that. But now we're getting into like implementation details that aren't useful if you're programming in C or Go. You need a bigger, heftier language to do that. Makes sense to do in Erlang, makes sense to do in Ada, but it doesn't make sense to do in Go. So I wouldn't worry too much about it. But the first argument, like if you have the same action no matter the current state, that's probably the biggest heuristic. And also ditto the inverse. If you have, if you know you're going to get the same input, know ahead of time, a priori, definitively you're going to get the same input no matter. What would it be? No, I don't think my brain is online enough to figure that one out. Sorry. Whoops. I didn't say anything. My brain is. You should prefer state first if whatever the opposite of that sentence is. And I don't see exactly what it would be. Sorry. I'm still booting up. All right, rip. Okay, here's the general structure. Here's what the general structure of a state machine is going to be like, right? We needed the outer loop, makes sense. We check the input first, and then we check the state second. This is why the state machine looks like this, and this is why the C code example looks like this, and like 90% of you are going to translate it to Go, and so what you're going to end up making is this. So you have the outer loop, which is the for loop, then you check the inputs, which are going to arrive as messages on some channels, and then you have a switch on the state machine states, and then for each of the states, do stuff or other stuff, yada, yada, yada. Make sense? So this is what like 90% of you are making as part of exercise 4, if you're programming in Go or any other message passing language. And now we are into the inevitable step 6, which is just question marks. So our blocks of inputs, we have one block of input, right? The do stuff and do other stuff. These are blocks of code, which need to be filled in with some appropriate functionality, whatever that is. So we have one block of code for each pair of input and state. So that's better than having one block of code for everything. So we've divided our program into lots of smaller blocks of code. So good progress. Smaller blocks of code, easier to understand, easier to get it right. We also want to have the possibility to divide these blocks further. It's not strictly necessary. You could just put all of the code inside these cases, but now you have a function that's 100, 150, 200 lines long, and maybe you go, yeah, yikes, maybe that's a bit much. Maybe you get 500 lines, and you go, big yikes. So we want to have some divide to go, what should go directly in these, like something needs to go directly inside these cases, otherwise our code doesn't do anything. But some things we want to have outside, probably as separate functions. And the question is, what goes in separate functions and what goes directly in the cases? And what is the condition for creating a function? Yeah, what is that condition? And then further on, is that principle generalizable? Does it apply for more than just state machines? Like, is the condition for creating a function something that applies for all code and not just this? We're going to be using a metric here on code quality, right? So does creating a function make the code better for some definition or better, or does it make it worse for some definition of worse? So now we're into the territory of like, what does quality mean? And that's, yeah, that's not necessarily a super easy problem to solve. I have hit a nice little break point here, which means having a break at this point makes sense. Questions so far, because yeah, tempo pretty high. Okay, so 15 minutes back at 14:10, and we're going to talk about when do we make functions and what is the condition, and we're going to talk about testability as that condition. All right, so goal is we want to make functions because functions are cool, and we want to separate our program into more functions because the more the better. And the question is, okay, how exactly, what is a function? What does it look like? How do we make them good? And how do we integrate this with our state machine design? And what goes in our state machine cases? And what goes in separate functions? And is it generalizable? So I'm going to take first, well, I'm going to take primarily an angle on testability here. And I'm going to justify that as code that is testable is good code. And I'm not going to say much more about it than that. But first, let's just talk about like making our code work, right? Because we need to make stuff that works, because otherwise we're not very good at what we do. So we have a hierarchy of stuff that helps us make stuff that works. So on the very bottom, we have like the compiler and the language. So if you have a type system, you can check that you're not writing stuff that doesn't make any sense. Spell checkers probably fall into this kind of thing. The formal verification, Christopher talks about this in his ADA lecture, which there's a video on if you want to watch that at some point and learn ADA better. But you can double check that your code actually does the right thing and not just looks like it does the right thing. So the formal verification exists. Then on the development testing, you're making stuff and you're running it and you're seeing if it does the correct thing. And you can formalize this with unit tests where you actually write a test and you pass some input to a function and you check that the output from that function is correct, so you're testing Singlish functions. And you can test sets of functions with the real world data. So, or that's kind of, yeah, you're probably going to be doing this as well on the lab. Then you have the end-to-end test, which is probably going to be the vast majority of your testing, which is just you're deploying it in the real world. You're pushing the buttons, you're seeing the elevator go up and down, and you're like, woo, fun. But if you want to, you're probably also going to test single functions, and you might not formalize it. You're just like, let's pass some input to this function, see what it does. Does it do the right thing? And if it doesn't, you fix it until it does do the right thing. Then you can do some runtime testing. So you can do some generic error handling, just like, did this go wrong? If it went wrong, try something else or do it again. Or you could do acceptance tests, which doesn't tell you exactly what went wrong, but it tells you that something went wrong, and it lets you deal with entire classes of errors, even things that you couldn't detect otherwise. We've been through this. We've been through process pairs and supervisors as well that can handle a complete restart of the program or a partial restart of part of the program. And then at the very, very top, we have redundant computation, things like inversion programming. You actually physically run multiple computers doing the same or a different program that does the same thing at the same time on the same, in the same space. So this is usually used in things like avionics, just to make sure that your flight attitude controller doesn't crap out. Then you have 3 of them and you compare the results and you go, if the results are within the same range, you know that something is wrong, and if one of them just produces something wildly incorrect, you go, well, you're dead now, because I killed you, because you're stupid. So redundant computation is kind of at the top of that hierarchy, but it assumes that you've done your runtime testing, and it assumes that you've done your development testing, and it assumes that you have a compiler and a programming language that is reasonable. So you probably wouldn't do your avionics computer with no error handling, no tests, and you didn't try it at all, and you wrote it in JavaScript. It's not a good way to make something that works. So our focus today is not so much on the runtime testing. We've talked about that. It's not on the redundant computation. I won't talk about that. Besides, Will has? Will? Not quite sure. And I'm not going to talk about programming languages and stuff at all in this course. Nobody will, because you should already know this. So we're going to talk a bit about the development testing part here today. So, well, what's the goal? The goal is to write something that mostly works in the first place. If it mostly works, then you won't have bugs. You don't need to detect bugs with acceptance tests, and you don't need to restart the thing all the time. And here are the things that I am not going to justify all that much. Testable code is good code. Anyone who hears like, you know what? Good code is untestable code. Anyone here is like, good code might be untestable. It might still be good code even if we have no way of knowing if it does the right thing. Is anybody going to show up with that claim? No? So I don't think it requires a lot of justification. It is fairly intuitive, but it is worth pointing out that I am not going to justify it in any formal way. But the informal way is you can't test it unless you understand it. And you can't, well, you can't be sure that it does the right thing unless you understand it. So if you're able to test it, you're able to understand it. In that case, it is more likely to be correct. Here's the bigger proposal, which is that the code doesn't actually need the tests. So the testing isn't actually the important part. The important part is writing it in a way that lets you test it. And this one is a bit harder to justify, but here we go. The act of structuring it in a testable way is the thing that provides the most benefit. That's the claim. Here's the reason. The reason is that the code needs to run on your brain too. So the code runs in 2 places. First it runs on the computer, and then it runs on your brain. And a bug is when the way the code runs on your brain is different from the way it runs on the computer. You had a model of what it should do, and then it did something else. So it means that your model of the code that you have written in front of you, how it behaves, your model of how it behaves was incorrect. So your model needs to be updated. So first, your model of what it actually does needs to be updated, and then you need to update the code so that it matches what you wanted it to do. So since this code runs in both places, the idea is if you are able to match the way it executes in those two places, it is good code. Because then you can read it and you can understand it and you can predict what will happen when you actually run it. So if you are able to write the code in such a way that your understanding of it is correct on the first try, it is good code. The only way to write it in a way that you can predict what it will do is if you're able to write it in such a way that you are able to see the inputs and the outputs you're able to predict what inputs would produce what outputs. If you're able to predict this, it means that you're able to write out some inputs that would generate those outputs. If you're able to write those inputs, then you're able to test it. So if you're able to test it, it means that you're able to you have sufficient understanding of what the code does, and you're able to express that understanding formally, and therefore it will more likely be correct. So it's a somewhat complicated argument, of course, but the idea is that if the code is testable, it means that you're able to run it the same way in both your head and on the machine. I'll just take a tangent on this and we'll take an example, and you'll see what I mean. Funny sound. So there are two main ways to debug. Who here knows about debuggers? Okay, good. Who here actually uses a debugger regularly? Okay, it's like 4 people. Who here uses printf when they're testing regularly? Okay, so literally everybody prints stuff out to the screen. So the question is, okay, there are two main ways of debugging. You have the good old-fashioned printf debugging, so you print them out as they happen, and then you have the proper debugger. And you go, okay, well, we have a tool called a debugger, and the act of programming is producing bugs and then hopefully fixing them. So you might think, okay, we have a tool called a debugger. The best way to remove bugs is to use the debugger, right? But in reality, most people, most of the time, don't do this, and the question is, well, why is that? Well, the reason is, and here's my argument, is that printf debugging is actually superior. And it goes back to this whole the code needs to run on your brain as well idea. So here's the first argument. It's not that interesting, but it's worth noticing that even if you have a debugger, the thing that you're trying to test is, well, you have some data that you're sending in and you have some data that you're sending out. And the data is just bits and bytes, and you can't interpret bits and bytes, so you need to format it anyway. And if you need to format it, you need to use printf, so you're back at square one, so you need to use printf anyway, even if you're using a debugger. So not a super interesting argument, but it's there. Usually when you're debugging, the problem that you're encountering is of the type, how did this happen? And not of the type, what is the current value of the stuff? And a debugger tells you the current value of everything, but it tells you the meaning of nothing. So what you really usually need is the history of things that happen. So you want kind of the phase space, you want the time component, you don't want the state space, you don't want to know what everything is right now, you want to know what they were and how this happened. So you want the history. And a debugger doesn't give you the history, not usually at least. It usually just gives you what things are right now, and that's not all that useful. And here is probably the biggest one. If you have a bug in your code and you need to add printfs to, or you're trying to debugging it with printfs, the only way to do this is to add the printfs in sensible locations. The only way to add the printfs in sensible locations is if you understand the code well enough to know what a sensible location is. So you're actually kind of rubber duck debugging with the printf statements and trying to put them in the tactical locations. And you can't put them in these tactical locations unless you understand the code, and the entire point of debugging was to match what the code actually does with what you think it does. And the only way to update your own understanding of it is to, well, analyze it. And the best way to analyze it is to just look at it and try to look at the code and not look at the bits and bytes output of the debugger. And then fine, that's the most important one. And then the final one, which is just kind of incidentally a thing that you could also do. If you have a log of all the inputs that occurred, and you printed them out, and you have the inputs, and you know what the wrong output was, and you know what the right output should be, then you can take those inputs that produce the bug and the outputs that are the results of your bug fixing and put them into a unit test and then actually start testing with proper unit tests. Good examples of this is probably in the whole request assigner code. So every time I had a bug in that whole request assigner, I added a unit test with what the result should be, and then I just started programming with the unit tests until it actually did the correct thing. So in the whole request assigner example, not an example code, in the code there, you will see that like the first half of the code is what it actually does, and then the second half is just unit tests, which are used for when I was programming it and when I was debugging it. So every time something was wrong, I added a new unit test. And the way they were generated was by just printing out stuff that was the wrong, printing out the input and the output for something that was wrong, and using that directly. So if you have a unit testing framework that is half decent, then printf debugging really supports that. So that's the tangent. And here are the examples. So first code, how would you test this? Or who would have any problems writing unit tests for this? So just checking, does it actually do the right thing? In fact, you might have a hard time testing it because it's so simple that testing it is kind of so trivial it's not even worth doing, right? So this is super easy to test. A plus B minus C, does it produce the correct value, yes or no? Well, you give it an A, you give it a B, you give it a C, you do the math in your head, and you go, what should it be? And then you check, does it do the thing that you expected it to do? And you go, yeah, it does the thing that you expected it to do. Happy times. So this is easy to test. Okay, so let's get something a bit harder. How would you test this one? So it's the same A plus B minus C functionality, but it's now written in such a way that it is, well, is it easier to test or is it harder to test? Give me a hand for easier. Give me a hand for harder. Okay, so the intuition is there, and we might not be able to express it yet, but well, here's one thing. We have these static integers, and the problem with that is that this B1 makes it so that the function does something different each time. So we need to remember what we did previously for the next test. And then we have the other one, which is the C1, which is outside the scope of the function, which means that if we have another test that uses the C variable, then the next test that uses this function might produce a result that we didn't expect. So the order in which we run our tests affects the output. And also, if we want to test it when B is 11, we need to call the function 11 times before anything happens. So that's, and also if you want to test it with B equals 11 two times, then we need to wrap around, so, or restart the program. So, you know, yikes. But of course, this isn't that bad, so we can make it worse. So let's make it worse. You know, I love this piece of code. I really do. Because it really shows how easy it is to make a complete mess with a small amount of lines of code. Right, so this one is actually really interesting because I don't actually know what the results should be. Because the B function, yeah, it returns C++. So it's going to take C, increment it by 1, and return that. The question is, what is the order of operations of the call to B and the minus C part? Does it evaluate C first, or does it evaluate the B function first? Do you know?
I think I remember from the compiler construction that it should go into the in function fn into the call of function B first, and then completely evaluate that, and then pass out again.
Yeah. So the idea is it should evaluate from left to right, basically. Yeah.
Right, it should go down in there first.
Yeah. As far as I remember, I think this is technically undefined behavior. If this is C code, this is undefined behavior. If this is C++ code, I think it's correct that it's left to right. So it depends on the language here. And if it's in D, it's definitely from left to right. So yeah, fun times. So why is this hard? Well, we have a shared variable in the C form, and we have an evaluation order problem, and then we have a testing the function. In what order do we call the functions? And then what happens if we call this same function multiple times? It's going to behave differently. So we have a lot of constraints here that makes it really hard to test this piece of code because it's going to do something else every time, and our ability to predict what it will do is really pretty bad. So if our ability to predict it is bad, it's because our model of what the code actually does doesn't match what the code actually does. And the reason why our model doesn't match is because we have a really hard time generating a model for this. And why do we have a hard time? Well, it's because of all these shared variables and interactions. Notice that, shared variables and interactions. Keywords. I like keywords. Please scroll. Oh, okay, there we go. So what makes testing hard? Well, we don't know where the values come from. So this external C value, it could be anything at any time. So we don't know what it could be because somebody else could be using it. So we have these implicit dependencies, but if we send C in as a parameter, we have an explicit parameter. So an explicit parameter is easier to reason about because we know where it comes from. It comes from the parameter list. There is no question. That's where it is. We also don't know what is saved. That's this shared variable. So if we call the function, if we change the order in which we test the function, it's going to change the order, or it's going to change the results. So we have some time ordering dependency here. And look here, we have time ordering problem. Where did we encounter a time ordering problem last time? Could it be in distributed systems? So we've actually shared variables even inside a single program is actually a distributed systems problem. And we have exactly the same problems with time ordering, and we have exactly the same problems of the management of state and rejection of reversals and all of that stuff. So if you're like, you know what, distributed systems was too easy, I want distributed systems within my code, then just add some global variables and boom, now we have more problems. So, if you want more problems. And then the interaction part. So the interaction with other components. We don't really know who else might be using this C variable, right? And then we finally, this one is not that intuitive, and it's worth explaining it's worth pointing out that you don't always, when we're talking about interactions, yes, you have the interactions that like this uses that variable and that uses that variable. But you also have an interaction with everybody who could be using that variable but doesn't. And this is the reason why global variables are so tricky. It's not that, okay, we have a global variable and it's used in 2 places, so it's not that bad. Right? You know it's used in 2 places, but anybody who's new, or you in 2 weeks from now, don't know that it was used in 2 places. You just know that it exists as a global variable and it could be used in 50 places. So you have an implicit interaction with all of those 48 other places where it isn't being used but could be used. And keeping track of that implicit relation of what is possible but isn't actually being done, that's the thing that makes it really hard to map a model of what the code actually does versus what you think it could be doing. Because you don't know yet. The only way you can know is to check all of the 50 places and see is it being used or not. And that's why global variables are so tricky. It's not just the interactions that it produces between things, yeah, that's a problem, but it's also the interactions that it could produce but you don't know about. So yeah, that's a key point and is really worth thinking about for like 5 minutes until you get it. So next question, what makes testing easy? Well, a function that only has inputs and outputs is easy to test. So if it has no internal states, so it doesn't remember the previous calls and it has no external state, so it isn't affected by somebody else doing something, then it's easy to test. So it does not modify the outside world and it is not affected by the outside world. And this is what we call a pure function. And this is a technical term and it's worth remembering. So a pure function is good old mathematics pure function. It is not affected by the outside world. It does not have an effect on the outside world. It's just inputs, just outputs, and nothing else, which means that it is entirely repeatable. And if it is entirely repeatable, then writing a test for it is easy, because if you want to test multiple things, you just repeat. Another thing that is easier to test is a function that is disassociated with its data structure. So if you're testing a class, the member function of a class, you first need to construct the class and give all of its member variables some value. So if you just have a function that isn't associated with its class, is just a function, then you don't need to set up the entire thing. You just need to set up the parameters for that function and nothing else. You just set up data and call the functions. So there's no setup for things that you don't need to set up, and no teardown for the things that you don't need to tear down. It's just data in, data out. So the goal is to test code with data, not to test the code and the data together. So this one is a bit less intuitive, but since you all haven't been poisoned too hard by object-oriented programming, this should be fine. Just think, testing a C function is easier than testing a C++ member function. And I think you'll see that intuition pretty clearly once you look at the code. So here's the generalization. The hard-to-test things are interactions, including potential interactions, shared ownership or shared variables in any kind, specifically shared access to modification. So if you have multiple things that can modify a variable, you don't know who's using it and what the value could be. The outside world is also hard to test against, because you need to set up the outside world. So if your test requires that you actually physically push the buttons, then that's going to be hard to test, because you need to reach over and push the buttons. But ultimately, the thing that is hard to test is modification. All right, so if you have somebody who writes to a shared variable, or you write to your own persistent storage, or there's some shared value of any kind, anything that is persistent and is being modified by someone else, especially, is hard to test. So anything that does something that persists, even if it is yourself, but especially if it is someone else. Make sense? Shared variables, hard to test. Persistent variables, hard to test. So this gives us a new set of goals. Our goals are on the modification front. That's the thing that was hard to test. We want to write code that's easy to test, so we need to work with the modification. We need to work with our data rights and our variables, and especially our shared variables, minimize those. So this gives us a way to split our code, right? We have code that performs modification, and then we have code that does not perform modification. And we want to make separate functions for code that does not perform modifications. Right? This is the criteria for creating a function. If you can write a function that does not perform any modification, write a function. Go right ahead, as many as you like, because these are inherently testable. So if you have a pure function and you have an opportunity to make a pure function, you make a pure function. There's no questions. You just do it. These perform no modification. They can have algorithms, they have if statements, they have for loops, they have all of that good stuff, lots of different paths. They can be hard to test. What these functions do is they find out what outputs should be set, right? But they don't actually do it. Then you have a set of operations that actually perform the modifications. So these are the things that actually do it. They write variables, they send messages, they open files to the outside world and all of that stuff. All the writes and all the modification, all of the destructive behavior, all of the things that makes it so that somebody else has new data to work with. So this idea, this point of splitting is, the idea comes from Gary Bernhardt. And he has a talk which is 30 minutes long, which I would probably encourage to the degree where I might even say it's mandatory that you watch this.
Can you link it?
Yes, the link is there.
Oh, it's there.
Yeah. So yeah, hopefully it's clickable in the PDF, but no guarantees.
It's not.
No, probably isn't, because Microsoft and PDF exporting. So I would consider this mandatory, and it goes into detail of exactly what this idea is and exactly why this is the correct way to do it. And because he does such a good job of it, I'm not going to repeat it. But the idea is, if you can make a pure function, make a pure function. And if you have some modifications, don't try to hide the modifications in external, inside a function. So don't like pass channels to functions and so on. I'll get an example of what not to do at the very end here. So here's first what you should do. You have a core. The core of your program is just a set of pure functions. And you can have as many as you like. And then the shell part, what is the shell part? Well, it's the thing that contains all of the modifications, all of the reads, all of the writes, all of the overwrites of your data. So this is the structure part of the state machine example. This is the for select and the cases in that inner switch. This is the shell. And in that shell, this is where you perform all of your destructive operations. Now, finding out what those operations should be, that's the core. And you'll see in the state machine example that you saw in exercise 4, this is how it is structured. Right? So you have choose direction and should stop. These are pure functions. And then actually stopping and actually moving, that is part of the shell. So the shell receives the inputs, it modifies the state, writes the output, but it doesn't figure out what to do. So all of the variables in communication go here. So the key here is that the things that you need to test are all of the branches, all of the different decisions, all of the algorithms, all of the things that makes it hard to understand what does a code actually do. Those are the for loops, the if statements, and all of that good stuff. If you are able to put all of these loops and all of these branches and all of these different paths that makes your code hard to get a mental model for, if you're able to put those in pure functions, you can create testable pure functions. And then all of the untestable part is the modification. But the untestable part, all of the modifications, it doesn't have any loops, it doesn't have any conditionals, or it has very few of them, a single if statement. And because it is so limited in the amount of conditionals it has, it is very easy to see if it does the right thing. You can understand a single if statement without writing a test for it, right? But a triple nested for loop with some inner ifs, testing that one with it's a bit more yikes. So the shell is hard to test. The core is easy to test. It's a pure function. That's what made it easy to test. But the shell is hard to test because it contains all the modifications. But it has no branches, which means that testing it is not strictly necessary. You can just by visual inspection see it does the right thing. That's the idea between the core and shell divide. So here's what it achieves. It separates decision and action. Right, so your code does two things, or the code has two features. It finds out what to do, and then it does it. And if you're able to separate out, you're able to untangle those two parts, then your code becomes better. It allows you to test the decision-making process without setting up the outside world and without affecting the outside world. So your decision-making process is, testing your decision-making process doesn't require you to actually do anything. It doesn't require any actions. It doesn't require that somebody gives you inputs, and it doesn't require that you have somebody to send outputs to. The hard-to-test part was modification. Modification and performing actions. And it transforms all modifications and all actions into trivial straight-line code, which doesn't require testing. And it also integrates perfectly with state machines. So the grayed out parts, that's, well, this is the core, or this is the shell. And the decision equals some pure function. The pure function there, which lives somewhere else, the collection of those pure functions is the core. And as I said, you can make as many of those as you like. And you look at this piece of code and you imagine that there are more inputs and more states. And you go, are you able to understand this? If this was choose direction, are you able to understand this? Yes. And then the question is, okay, but it assumes that choose direction actually chooses the correct direction. And if you have a pure function for choose direction, are you able to test that it actually chooses the correct direction? Yes, you are able to write this test. And you don't need to set up an entire elevator. You don't need to set up a network. You don't need to open files on the disk or anything like that. You can just test the function on its own. So you have a testable function, and we like testable. And then you have something that is so simple that it doesn't need any test, and we like that too. So this is the way to, this is the boundary for when do you make a function is it a pure function? That's it. So don't get this backwards. I see a tendency to get this backwards, and I know where it comes from, and I don't like it. So here's what not to do. You can run your for loops, your triple nested for loops with the internal if statements and gotos directly in these select cases. Don't do that. You go, well, this block of code looks very large. I will make a function because the line count is too high. Line count? Line count isn't a code quality metric. It's not like, oh, it's too big, my eyes can't look at that much at the same time. It's not. Your understanding isn't limited to your physical field of view of your eyes. That's not how you understand code, by counting lines. Right, so the goal is to make code that runs the same on your brain as it runs on the machine. And, well, if your brain is tied directly to the field of view, the console field of view of your eyes, you have other problems. Get glasses. Don't pass interactions in a bucket brigade. So if you have a function that takes a channel as a parameter inside your state machine, you know you fucked up. So don't do that. And then don't bury modifications to state and interactions to the outside world in these functions. So you're like, oh, the line count was too long. I need to make a function because line count was too long. Oh, I need to write some states, and we're deep in like 3 levels deep inside some functions. I called some function that calls some function. I'm just going to write to my shared variable that's in global scope. And also send a message to the network because I can, right here, right now. And don't do that because it makes your code completely incomprehensible. But you might think, oh, but I'm supposed to hide the implementation details, and I'm supposed to do encapsulation, and I don't really know what the word means. So I'm supposed to hide things so that you can't see them. Here's the hint. Hiding is bad. Well, hiding is bad. Hiding is lying, right? I know there's this meme about hiding implementation details, but hiding means that there's something that you don't want someone else to know. Otherwise, you wouldn't be hiding it. So the only reason to hide something is because you've done something that you shouldn't be doing. And hopefully when you're programming, you're not doing something you shouldn't be doing. You're doing what you should be doing. So instead of hiding, try to expose. Right? You're trying to write code that is written in such a way that you are able to get an understanding of it as efficiently as possible. And if you need to dig because somebody's been hiding, then the rate at which you're able to generate that understanding of the code is very low, because you need to try to find all the things that somebody else was hiding. So hiding isn't the correct word. It definitely has the wrong intuitive and emotional content. It's not. It might be technically correct, but it doesn't mean what it needs to mean. We need to use a different word than hide implementation details. So whenever you see that, you know that somebody hasn't thought very much through it. We want to be explicit about what the code does. The more explicit we are about what the code does, the easier it is to understand what it does, because the code tells you what it does and you go, I understand what it does. If the code is like, I don't want to tell you what I'm doing because I'm hiding implementation details, then there's no chance. You're never going to understand it. Because here's the key. The hard to test part, that's the modification. The thing, what your program actually does, if it does something, it needs to modify something. Either it needs to send data to someone else or it needs to write something to the outside world. So the hard to test part and the hard to understand part and what it does, those are all the same thing. And so the only way to make code that is understandable is to expose that hard to test part as much as possible. So expose the modifications, make it as clear as possible exactly where it is and what it is.
Doesn't this kind of go against the code quality point of abstraction?
Does this kind of go against the code quality point of abstraction? Yes, and also no. Because, okay, abstraction as a word is a word that I don't really like because it's so hard to define that people end up talking past each other. But we can take a sidetrack on it and improvise a sidetrack. I'm going to talk about this more in like 2 weeks probably. The idea behind abstraction is that you're not hiding things. You're not layering things. That's not what abstraction means. Abstraction means that you are giving yourself the permission to forget the details. And the way you give yourself permission to forget the details is you go, okay, I don't need to know the details right now, but it's easy for me to find them if I need them. But usually I don't need the details, but sometimes I do. So if you have a hammer, you don't really care. The abstraction is nail-hitting thing. And you don't care about the implementation details of exactly the structure, the length, the height, the width, the weights, the weight distribution of the hammer, until you do. And when you do care about it, you can inspect it and go, oh yeah, there's a detail about this hammer. It is really good at pulling out nails, or it's really bad at pulling out nails. So you haven't like, oh, it can pull out nails, let's just kind of tape that over and try to hide the implementation details. No, your brain doesn't hide the implementation details. It doesn't see the hammer and be like, I can't see it because it's hidden. It goes, I don't need to look at it. I don't need to understand it yet. My brain can kind of go, hammer, generic hammer. And so the details aren't hidden, but the details are not observed. That's what abstraction is. And so it's a really hard concept to understand because we don't have a better word for it, and the mechanisms for how it works is so tied to like the neurology of what your brain does. Like literally the only thing your brain does is abstraction. It creates frameworks of references that lets you see patterns in the world instead of actually things. And then we need to go into like the neurophysiology of how your brain observes the outside world. And then you need to go into like the metaphorical substrate of thinking itself. And so you can't talk about abstraction as a word before you understand metaphorical substrates, and you can't talk about it until you understand the neurology of how your brain works. And so that's why I don't like the word, because that's a lot of ground to cover to understand programming. So instead of abstraction, use generalize as a much better word. So you're not trying to hide implementation, you're trying to generalize for anything that could provide that implementation. Let's see if we can cover this in 10 minutes. Let's talk about interactions. All right, so the hard part in our code was modification, but another, part of modification is interacting with other components. All right, we're sending messages to them, and they do something with it, including storing the variable. So that's an interaction. And, we need to test those interactions, and we need to figure out what exactly are those interactions. Like, how do we communicate from one module to another module, and what exactly is a module? So on testing interactions, our components, whatever our components are, let's just say that we don't know that our components are processes yet. They could be processes, they could be objects. Just keep them both in mind. Like, we haven't made a decision on this yet. So the idea is, can we, from a testing perspective, inform what the decision should be? So our components interact, and we need to test this. In order to test an interaction, or in order to test a write, do we need to set up both things that are interacting, or can we set up only one of them and have it interact with a fake thing that isn't the real thing, it's just a fake replacement? Is this possible? So we can use proxies, mocks, stubs, etc. And if you're interacting with a fake thing, this gives us isolation, right? So you're not actually writing to a database, you're writing to a fake database and just logs it and goes, yeah, that makes sense. So that gives you isolation from the outside world. You can test one thing against a lot of fakes. You don't need to set up everything, because the moment you need to set up this one, you need to set up whatever that one interacts with, and now you need to set up the entire program. So in order to get isolation, you set up fakes instead of the real thing. The drawback with this is that it requires setup. Obviously, you need to set up the fakes, and you're not testing against the real thing. And the moment you're not testing against the real thing, there is a chance that your fake components go out of sync with the real components, and you're actually not testing the program, you're just making sure that, you're testing against fakes, and the results you get back are also fake. So if your test double models the wrong behavior, then, your test is going to pass, but it's going to do the wrong thing. So we have a problem here. Like, we need to interact with the real things in a real way, but we don't want to set up all of the program to be a real thing. So we have a boundary problem here. So our components have some kind of interaction surface. They have member functions, they have member channels, they have member something. When we're testing a component, first principles thinking, when we're testing a component, we have to use that interface. because that's, in order to test it from the outside, we need to use the interface of the thing. And the interface has some requirements for what it accepts, right? The member functions can't take random parameters, they can only take the things that it can take. And when we're testing it, we want to test it with some data that is real enough that we can actually test that it does the right thing and not just garbage in, garbage out for our test. So we need to give it real types, we need to give it valid data, we need to give it all of that good stuff. But we also want it to be non-destructive, because the moment it's destructive, then the order in which we test them becomes a problem, and our ability to predict what it should do becomes 0. So if the test order matters, then we may as well just do a full-on end-to-end test and not do any kind of unit testing at all. So what's the conclusion? The conclusion is that our interactions with other components we can't call member functions to interact with another component, because the moment we call the member functions, we need to set up the object whose member function it is. And it needs to model that behavior correctly, but it can't be the real thing, but it needs to be real enough, and we need to set it up. So the boundary can't really be a reference. The boundary has to be just a value. So it needs to be just data. So the only way to write a test that does something useful is to have data in, data out. And if your test is more than just data in, data out, it starts invoking behavior, it starts actually performing the modifications and all of that, then we're in trouble. And this is why object-oriented programming is so hard to get anything useful out of. So here are the 3 big problems with objects which message passing solves. This might be controversial for some of you because it means that you've spent half a year learning something that isn't useful. But, sadness, such is life sometimes. So an object doesn't do anything. That's the first thing. Our thing doers, the things that are the tasks in our program, yes, they have data, they have state, and they have inputs and outputs, which means they have functionality. So data plus functionality, you go, data, function, combine them together, boom, object, right? So this is literally all of programming, and you might go, data plus code equals objects, and object equals good. The problem is that, remember, functions don't do anything. A function on its own doesn't do anything before it is being called, and something needs to call it. And what is the thing that calls it? Well, it's a thread, or it's a process, something like that. So the function must be processed by a process running on a processor. Before then, it's nothing. So functions don't do anything. Objects have member functions, which means that it has data, which doesn't do anything, and it has a bunch of member functions which don't do anything. So the objects don't do anything. If an object doesn't have the ability to do anything, it doesn't have any agency. If it doesn't have any agency, then since it doesn't do anything, it can't have any responsibility. So the responsibility for whatever the object does is handled by whoever calls the member functions of the object. It is not handled by the object itself. This is a key realization. Right? So the thread that uses the object is the thing that does something. The thread that uses the object is therefore the thing that has agency. It is also therefore the thing that has responsibility. The object itself doesn't have that. So it is up to the user of the object to use it correctly. It is not up to the programmer who is programming the object to make sure it is being used correctly. It is impossible for the programmer who is making the object to make sure it is being used correctly because they are not responsible for its use. This is dangerous, because now you're making code and you have no guarantees for that the code that you have written is being used correctly. And you have no guarantees for it being correct in any way because you can't guarantee it because it has no agency and therefore it has no responsibility. So that's the first problem. Yeah, we're not done. Second problem, reference hell. Objects interact through their member functions. So in order to interact with another object, you need to call its member function. In order to call its member function, you need a reference to it, which gives us 2 options. If you have two objects that interact with each other, you must either have a circular reference or you must have a strict tree of some kind. So here's a circular reference. A interacts with B in order to call its methods, and B interacts with A in order to call its methods. So you need to set up some circular references. There is no elegant way to set up circular references because they both need to be started at the same time in some way, which means you need a factory. I'm sure you've been, who here has done factories? Nobody, so you never actually learned object-oriented programming. Well, that's good, because there's less to unlearn in that case. Here's the alternative. Let's say you have A and B at the bottom here as leaf nodes of a strict, you don't want circular references, so you only have a tree. That's the only way you can do it. So in order for A to communicate to B, it needs to first kind of hope for the parent's attention, and then hope for the parent's attention again, and then it will hopefully send kind of bucket brigade that message down to B. So you need 4 operations, 2 implicit and 2 explicit, just to get a communication across to B. So what do you do in reality? You say, fuck it, I need a reference to B so I can communicate with it directly. And now you have a circular reference hell again. So you can't really structure an object-oriented programming or an object-oriented programming in any sensible way. It's just not physically possible. So it's impossible to initialize circular references in an elegant way. And communication between leaf nodes is impossible to do in an elegant way. So the only way to do this is with polling and bucket brigading of some kind. So you don't pass a message directly, you pass it through all of these indirections. And we also have the problem from the first code from the first point is that a single object doesn't do anything. So when you have objects that interact with each other, they also don't do anything. So if everybody is irresponsible for their data because nobody has any agency, and everybody is tightly linked because everybody has references to each other at some capacity, then all of the irresponsibility of your program becomes transitive. So again, the thread is the thing that does something, and the thread has a bunch of objects that all interact with each other, and you don't know what those interactions are, and when you're programming one of them, you don't know who's using you in what way. Yeah, this is not going to be a nice way to structure your program. It's never going to work. And then finally, no, we're not done. If you have a reference to an object, you have access to all of its member functions. Now, typically, you don't need access to all of the member functions. You only need access to 1 or 2. Typically, you would use different subsets in different places. So, example, on the elevator. The thing that generates a table of orders so that the state machine that executes it can execute that table of orders. The thing that generates the tables of orders and sends it to the state machine, it doesn't actually need to be able to send it a new floor or send it a door close timeout. But if that state machine is formulated as an object, and we need a reference in order to get that, here's a new order table member function, we also get access to the member functions to give it a new floor or to give it a door close timeout. We don't need that. In fact, it would be better if we didn't have that. Our code would be better if it was impossible to provide or cause behavior that we're not supposed to cause. So if we could give it not an all or nothing interface, but like exposing a partial interface, that would give us better code. So our final problem is that enforcing correct usage requires manual inspection to see who actually uses us versus who can use us but doesn't use us. So it's exactly the same problem as with shared variables, but now it's not a shared variables, it's shared member functions that we don't need to share. So the moment we make it so that others are responsible for what is done to us, we have a bad time. We don't want someone else to be responsible for what is done to us. We want to be responsible for what we do. The moment we can get the responsibility in one place, and we can be responsible for it, and we can expose partial interfaces to everybody else so that they only can do what they need to do and nothing else, then our code becomes much easier to understand. So what happens? Well, if we use processes, we don't have any problems of these kinds. The processes are threads, which means they do something. They have agency, which means that they can have responsibility. When you receive a message, you are responsible for modifying your own data, which is local to you, and nobody else can change it. And so therefore, we can have responsibility, which makes it easier to understand what this piece of code does, because we are programming our own thing, and we are responsible for it, and we have control over it. The interactions are on channels. The channels are not members of the threads. The channels are passed in as parameters to the threads. So since they're not owned by the process, they can be created outside, and they can be passed as parameters. So the reference hell is just immediately gone because you don't need references to the process, you only need a reference to the channel, which gives you a single interaction point. Hey, that's the final problem. You can get a single interaction point at a time. You can expose one channel at a time. So the thing that sends the order table, it has a channel that lets it send an order table. It doesn't have access to the channels that lets it send a new floor or a door to close timeout. And since it doesn't have access to those channels, because it never sees them, it can't do the wrong thing. So it can't do the wrong thing, and if it does do the wrong thing, we are still responsible for making sure that we handle it correctly. Not somebody else is responsible for not doing the wrong thing in the first place. So the question is, okay, well, how come object-oriented programming is such a big thing and process-oriented programming and multi-threading and message passing is such a not a big thing? How did this happen? So here's the core misunderstanding which happens all over the place. The misunderstanding is that people think that there is a duality between code and data. Right? So you have code which does something, and then you have the data which doesn't do anything. And that's not right. Code doesn't do anything. Functions don't do anything, right? Code is just data that tells you how to make more data. Before it is being run, it doesn't do anything. It just tells you how to do it. The real duality is between execution and data. This is incidentally what object-oriented programming meant originally, as defined by Alan Kay. Object-oriented programming, to me, means only messaging, message passing, local retention and protection. Okay, that's our local variable inside our local state machine or our local process. Our state process, good, there's our state machine. An extreme late binding of all things. Okay, that one's unique, that one's different. You're familiar with early and late binding? No? Okay. So late binding in this case means that our process is able to accept any message of any type before we don't know what it could send us before it has sent it to us. So that wouldn't be channels, that would be a message inbox. So what he means here is Erlang, basically, an actor model. So anyone could send us anything, and it's up to us to handle this correctly. So the responsibility lies with us. The difference between object-oriented programming, as defined by Alan Kay originally, and a process-oriented program is that we don't have late binding, we have early binding. So we know what others can send to us because we have specified what the channels are in our interface. And the channels also specify the data types. So we know what can be sent to us. So we don't need to be able to handle the things that we don't know about. That's the only difference. He also has a famous quote for, when I invented the term object-oriented programming, I did not have C++ in mind. So this is what object-oriented programming meant originally. So you could argue that current state of object-oriented programming is a perversion of object-oriented programming, or POOP as an acronym. So, well, let's continue after a 15-minute break. We're going to then figure out exactly how do we divide a program with multiple things to do into separate tasks. What is separate in this case, in this context? We have now thoroughly established that object-oriented programming is literally useless, as in it doesn't do anything. So we need threads. So our design pattern or our design infrastructure is going to be a bunch of threads interacting with message passing, because that is the only way to program a program with separate pieces of responsibility. The question is, what are the separateness in those pieces of responsibility? But first we need to figure out exactly how they interact and, well, yeah, we need to figure out exactly how they interact and how we structure it in a sensible way. So let us reintroduce the thing doer, the thing that does. So it has data that needs to come in, it needs inputs, it has some local data, that's its states, and it needs to send some data out. And it has a loop because it's doing something, so, well, there's a loop. So it has a self-reference. All right, we use the current version of the data to create the new version. It has a data flow. Data has a source, an input, and a destination, and it has an interface. So there is some boundary between what is on the inside of the thing doer and what is on the outside of the thing doer. The data needs to come in and the data needs to go out. And what does come in and go out mean, and what does it look like in code? So the question is, why channels? Why did that end up as the correct solution? Because the alternatives, well, they exist. I don't know, call the function. Right? If we call the function and we get some input, then we're doing it, but the data needs to live somewhere and it needs to get to us somehow. So we have two ways of doing the control flow here. Well, two options. Well, we have two data flows, right? Or start that sentence over. Okay, so there are two flows here. We have the data flow, which is pretty simple. It goes from left to right. So data comes in, the data goes out. And then we have the other flow, which is the control flow. So how do we get the data that needs to come in, and how do we produce the data that needs to go out? Like, what exactly is that mechanism? So the data flow, that one's fairly obvious. The control flow is not that obvious, but we have two options here. So the retrieve way is that we actively look for the inputs and we go, okay, what was the input? Read the input, get the input, fetch the input. So we have a getter function of some kind, possibly. We're active in the input side and trying to get that input, which means that somebody else who is trying to get things from you, the way they get things from you is that they get with a getter, and they're pulling your values, and they're trying to actively read your inputs. So you're passive in your outputs and then active in the inputs. The other way is to do it with message passing. So somebody sends you the data, so it comes to you as part of a message. So you're passively listening for the inputs, and you're actively sending the outputs instead. So that gives us two ways of, we can either align the control flow with the data flow with message passing, or we can kind of contraflow it with polling. And so the argument is, well, the argument is instead of kind of having them in contradictory directions, we want them to be aligned. And why would we want them to be aligned? Is it just an aesthetic decision? Maybe. But the less aesthetic reason is that we want to be active in our outputs, right? So in order for our task to do something, it needs to do it. In order to do it, it's something it's producing. And the thing it's producing isn't the input. The thing it's producing is the output. So it makes sense for our code functionally or functionality to be active participant in what it makes and not be an active participant in what it needs to do or what it needs to read in order to make it. So we want it to be active in the outputs. And we cannot pass results to somebody else with a function because then they aren't active, then we are active for them. So in order for them to be responsible for what they receive, we can't pass things with a function, which means the only way we can do it is with message passing. And that's why we prefer message passing. Even if we have separate processes, you could argue that, okay, there are separate processes, therefore they have unique responsibilities because they actually do something. But you also need the message passing, otherwise you can't be active in your outputs. And if you're not active in your outputs, you're not actually doing anything, you're just kind of spinning. So the interaction points between our thing doers, between our processes, they have to be channels, they can't really be anything else. Or, I mean, they could be some other message passing mechanism, but you need message passing of some kind. Because again, as always, remember, functions don't do anything. So with that final little block, it gives us the general structure for what our Go program or other message passing program is going to look like. This is the most general thing. Your program will consist of a lot of these things and not much else, right? You have a thing doer, it takes channels as parameters so that you don't need to spawn circular references. It has some amount of local data, typically one struct, maybe more, maybe a map, maybe an array of some kind, but usually one or two pieces of local data. And then it has a for select. And then for each of those things, each of the messages that you can receive, you have a select case, and then you possibly inside that you have a switch on a finite state machine state, but that is not strictly necessary. Use the state machines if you have some data that needs to be minimized, but don't use a state machine if you don't need a state machine. It produces some output, and it reproduces some local data, overwrites it. That's going to be the general structure for your Go program. If I see a Go program that's not this, then we're going to work on it and we're going to restructure it until it looks like something like this, because this is the only sensible way to write a process-oriented program. The question is, okay, what separates one thing doer from another thing doer? That's the final piece of the puzzle. So let's get to the final piece of the puzzle. How do we split a program into multiple processes? Again, let's just set up some goals, hopefully from kind of first-ish principles. Our program has to do something. Well, duh. Okay, so we want to split the program into several smaller parts. Why? Why can't we just do everything in a single main function? If we are able to split it into smaller parts, these are what they would be doing. They have to interact with the whole program. So they need to be able to interact with other parts of the program. They need to do something on their own. Here's a key idea. This goes back to the kind of the abstraction question. Why do we make them separate things? Well, because they are doing their separate thing. How do we know it's a separate thing? It's because we're able to give a name to it. So if we're able to give a name to it, it indicates that the thing that it produces is a thing that exists in our mental model. So if we're able to put a name to it, it's an indication that it's a good thing. And if your name contains an and, it's an indication that it might be two things. So what does it do? Well, it produces new data for itself, and it also produces new data for others. So these are just the goals for a single thing, right? So our single thing needs to produce something for someone else. And the thing that it produces, it would be nice if we're able to give a name to it, because if we're able to give a name to it, it means that it's a thing. It actually does something. The thing it does is something that exists. So that would be nice. But these are very vague goals. They're more like zeroth principle goals more than first principle goals. So let's just think about it in terms of its extremes. Like what happens if we don't do this at all, or what happens if we do this in such an extreme way that it might be too far. And if we're able to see what the extremes are we able to find what the middle could be? So the one extreme is to have everything in main. So you have a single God process and it has all of the data. And in order to make functions, you need to make a bunch of pure functions, and all of these pure functions, they need to have all the data passed explicitly as parameters. So you basically program the entire elevator project directly in main with one giant state machine. So it handles order distribution, order assignment, order execution, the door, the motor, everything is handled in one single giant switch case. And you might go, well, that doesn't sound like fun, but it is possible. You could do that. Nothing's stopping you other than your conscience. But you could do this. So this is a possibility. It will work. So we have one thing that modifies all of the data, right? We have one God process. It has all the responsibility, and it does all of the things. So the main function is responsible for all of the modification. All right, makes sense? Single process does everything. And then on the other extreme, well, our code there's a bunch of persistent data that needs to exist in our program. What happens if we take each piece of data and spread them out as much as possible? So one piece of data goes in one thread, and another piece of data goes in another thread. So if we're moving or not, it's a Boolean, it has its own separate thread. What direction we're moving in, it's a 3-valued thing. It's a piece of data, it exists in its own thread. Right? What floor we're on, it's a piece of data, it exists in its own thread. Like that extreme, we're talking like completely full on, bring it on, everything in its own separate piece of, in its own separate process. So in order to do anything here, we need to get the data out of that process. We need to make some modifications, figure out what to do, and then we need to send it back what that value, the final value should be. So we need some getters and we need some setters. Right? So the only time that we can modify something is that we want to modify several things at once. In order to modify several things at once, we need to then talk to multiple processes at the same time and be like, here's the new value for you, here's a new value for you, here's a new value for you. And the only way to figure out what that new value should be is you need to getters. So you need like, hey, I need your value, I need your value, and I need your value. So multiple participants in and multiple participants out. So in order to do this, you need all the getters, you need references to them, you need all the setters, you need references to them. So there's a giant tangle of interactions there. Now, obviously, these both suck. Right? Putting everything in one place and putting everything all over the place, these are not good solutions. It should be fairly intuitive that these are not great. What is less intuitive is that they suck for the same reason. Do you see it? Do you see what the same reason is? This one is hard. And I'm not like talking like, oh, the code quality isn't good. That's the same reason. No, I'm a bit more specific than that. Okay, let's see what we can make out of it. This one is hard, and I have a hard time with it myself. So hopefully I can explain it. We'll see. We'll see. So what is the same reason? The surface area for modifications is large. A comment in the chat here. The reason why they're the same is because they are actually the same. Well, yes, good. You see it. Okay. So the surface area for modifications is large. Right. What do we mean? Well, in the God objects, it is responsible for all of the things. And in the thin spread, everybody is responsible for their own thing. So in the God object, you need to untangle the actual modifications from the potential modifications. Let's say we arrived at a new floor. You need to update the floor, but you don't need to update anything else. So the list of who is alive on the network, the floor arrive function can modify who is alive on the network, but it doesn't make sense that it could do it. So you need to untangle the actual thing from the potential thing. Now in the thin spread, it's exactly the same thing. You need to be able to access all of the pieces of data that exist, and therefore you need to access all of the processes. So you need to untangle which ones are you actually including in your participation here, or which ones are not participating. So it's the same problem. And then we're back to the thing that you discovered in the first exercise when it comes to ownership and responsibility. The only way to have responsibility is if you have unique ownership. And the only way you can have unique ownership is if you also have unique responsibility. So these are two sides of the same thing. So in a God object, you have one thing that is has ownership of everything, and it has all of the responsibility in the entire program. So all of the other blocks of code, those are just going to be pure functions, and they obviously don't have any responsibility. If you spread everything out thinly, then you have spread ownership. So the ownership is spread everywhere, and nobody has any responsibility for anything explicitly, because in order to have responsibility, then you need to, well, you're responsible for multiple modifications in multiple places at multiple times from multiple sources. So nobody's responsible, everybody's kind of overriding each other at all times. So any block of code that has access to one thing has access to basically everything. So in both cases, you as a programmer need full awareness of the entire program to understand anything at all. The only way you can understand any part of the program is to understand the whole thing at the same time. Does that make sense? If you spread everything out, you need to know where everything is, and you need to know who participates. If you centralize everything, you need to know what the piece of data is, the giant blob of data. You need to have full control over the giant blob of data and make sure you don't mess it up. So in both cases, you need to have full awareness of everything at all times. And in both cases, the only way you can get that awareness is to untangle what is actually happening versus what could happen. So let's see if we can find the middle point of these and see if there is kind of a peak optimality where code quality is at the maximum at some middle, and what exactly defines that middle. So what was the hard problem again? Well, okay, so what's happening? When we are writing data, shared modification. So we're modifying multiple things in multiple places. Modifying multiple things in multiple places is only necessary if we have multiple places. Right? So the inverse of that, or the corollary of that, is that grouping data so that you're modifying multiple pieces of data at the same time is only necessary if you're actually modifying several of them at the same time. So grouping the floor and the direction together, that makes sense, because you're modifying the floor and the direction together, right? You're moving up to the next floor, so it makes sense that those are collected together. The floor and the list of who's alive at the network, you arrive at the floor and somebody else is alive on the network, it doesn't make sense. Somebody else joins the network and that teleports you to another floor, doesn't make sense. So those two don't need to be grouped because you don't need to be modified at the same time. Do you see this one? This is the key. If you need to modify them at the same time, it makes sense to group them. If you don't need to modify them at the same time, it does not make sense to group them. On the input side, we get exactly the same arguments. Data duplication is only a problem if there is a synchronization requirement. So you get data, the data here and the data there is different. Is that a problem? No, only if there is a synchronization requirement, and they have to be the same because there's something that requires them to be the same. What is the thing that requires them to be the same? Well, the only place where we can observe a desync is in some output. So the lack of synchronization is only observable in an output. How do we perform synchronization in an output? Well, we handle it by grouping them. So you can only observe some data going out of sync in different places in your program if it is in an output that is produced somewhere. The only place you can produce, or the way you produce outputs is by grouping things that need to be modified together and ungrouping things that don't need to be modified together. So this becomes a nice criteria for splitting. The data grouping. If you have two pieces of data that need to be modified together to give the program correct behavior, like you need to modify the floor and the direction together, and the door timeout together, so that you don't start moving before the door is closed or something like that. If you have a collection of data that needs to be accessed together, no, modified together, not accessed together, but just modified together, then they should be in the same place. If you have data that needs to be accessed together, that's not a problem. Reading isn't the hard part. Writing is the hard part. Writing produces a modification. The modification is the problem. The data duplication isn't the problem. So if you need to duplicate data, that's perfectly fine. You can get copies. Get copies if necessary. Duplication is preferable to overgrouping, because you will find that, oh, we have a duplicated data. The data exists in two places. Somebody needs the list of, all right, the distribution process needs a list of everybody who's alive. The assignment process also needs a list of everybody who's alive to figure out who is eligible. Yeah, we have duplication. Is that a problem? No, it's not a problem. Because the alternative is that the assignment process and the distribution process become one thing, and they don't need to be one thing, because they don't write to the same data. So once we've figured out what groups of data are natural as a result of being modified together, not being read together, but being written together, once we have these groups, each group goes in its separate process. So this is the modularization criteria. Right? Data grouping on its own is the one single modularization criteria for a process-oriented program. Now, possibly you could try to reduce that data and reduce it into a state machine. It's not technically necessary. Sometimes it's useful, sometimes it's not. Okay, here's an example from the elevator systems. Let's see if we can kind of bring the intuition out. The elevator system can at least be separated into three parts, and I've said this to basically everybody. Oops, assignment, distribution, and execution. Why? Because they write to different things, right? So finding out who takes an order, we don't need to be able to move the elevator up and down to find out who takes it. We don't need to be able to talk to the other ones. We just know what they're doing, and if we know what they're doing, we know where they are, we know what their costs are, and therefore we can find out. So we don't need to talk to them to actually do this. Now, if you have an auction system, you need to talk to them. So that complex those two. All right, and an auction system is like, hey, what's your cost? Hey, what's your cost? And then you get responses back. Then you need to communicate. So then they're the same thing. The distribution side, sharing order information. So we know that an order exists. So let's say we find out first, we know that there's an order exists, and then somebody else, somewhere down the line, we figure out who's supposed to take it. But we first need to spread the order across the network. Do we need to assign it to spread the order across the network? No. Do we need to be able to move the elevator up and down to move it across the network? No. So therefore, they're separate. And finally, execution. Do we need to be able to find out who takes an order when we are executing an order that has been given to us? No, of course not. Do we need to be able to communicate on the network that a new order exists when an order has been given to us? No, of course not. So therefore, these three can at least be separated into separate parts. Does that make sense? The criteria for this separation is the grouping of data that needs to be modified together. Here's another example. The obstructed door. I didn't include this in the state machine example at the top. So let's see. Here's the reason why you don't have to redesign the state machine is because it's a separate state machine. So the door can fail to close due to the obstruction in the door or somebody pressing the same button over and over. I'm not 100% sure if the second one is actually part of the specification. I don't remember. But let's just assume for now that it is. Now, operating the door, opening and closing the door. Does that require that we are able to move the elevator up and down? Does it require that we are able to read and write to the order list or the order table of active orders? No. Therefore, the door obstruction mechanism can be handled as a separate state machine. It doesn't need to be integrated into the main state machine. It can be a separate thing. We can have a separate state machine for the door with its own inputs, its own states, and its own outputs. Right? So we send, hey door, please open. I want you to open. And it goes, yes, I will open. And then the obstruction is an input, an internal input here, which I didn't note down. So the obstruction switch triggers, and the door goes, oh, I am stuck. And because I am stuck, I will not send you a door closed message. And then the moment the door is unstuck, the door goes, hey, I was able to close the door, you are ready to go. And if the door obstruction is active for a long time, it goes, you know what, I was never able to close the door, here, have an error, I failed. Maybe I'll succeed later, but for now, I am stuck. Just figure out what to do. So the door can be its own separate state machine. And the same thing for the motor timeouts. So the motor goes, oh, I want you to move up. And the motor goes, yes, I was able to arrive at the floor, or it goes, I was not able to arrive at the floor. It's exactly the same kind of state machine. It's either stopped, it's moving, or it's stuck. So the same three-state state machine for the motor functionality as well. Now, emergency stop, for example, that's not going to be the same thing. Not that it's part of the specification, it's not, but if it were, how would you handle it? Well, you can't have an emergency stop that goes, oh, somebody pressed the emergency stop, open the door. We're still moving, so we need to stop the elevator, we need to open the door. So the emergency stop functionality needs to be able to move the elevator or stop it from moving, and it needs to be able to open the door, and it needs to interact with the timers, and maybe it needs to clear the order lists or something like that. So therefore, since it has a deep interaction, it needs to be modified together, and therefore it needs to be integrated into that state machine. It can't be a separate thing. Make sense? Good. So, today's summary. A program consists of several tasks. Why? Because it's easier to program it when we are able to separate our program into multiple things so we can focus our attention at one thing at a time. The only way we're able to focus our attention at one thing at a time is if we are able to be uniquely responsible for that thing at a time. And the only way to do that is if our tasks are processes. So our tasks have responsibilities. Our tasks, in order to be able to actualize those responsibilities, they need agency. They need to be threads. They need to be processes. What goes in one process versus what goes in another process is determined by what set of data needs to be modified together. If things need to be modified together for the functionality to be correct, it's one thing. If they don't need to be modified together, they can be two things. Data duplication be damned, we can get duplicates wherever we want them. Once we figure out what tasks our program consists of, we create an independent process for each of them. And possibly, we convert each one of these into a state machine. Maybe that's not necessary. Maybe it's so simple a state machine is overkill. Then we wire those together with channels or queues. Don't wire them together with function calls, because then we're kind of reaching into our inputs, but we want to reach out into our outputs and produce things and actually make things. We want to be active participants in what we're doing. When we've made a single process, we want to divide the work of that process, the code blocks in that process, and we want to divide that into two parts. The imperative shell, which is responsible for all the inputs and all the outputs, and all the data re-overriding. And then the functional core, which is just a collection of pure functions where we can create as many as we want. They don't matter, they're easy to test, but what they do is to find out the functional core finds out what to do, which is decision making, which needs to be tested to make sure it's correct. And the imperative shell is no decision making, it just performs the decisions in a straight line. So it doesn't require any tests. And then if it's possible, the data that we are responsible for, if possible, we can minimize it. Typically, if we have a bunch of booleans, if we have 4, 5, 6 booleans, then we go, looks like a lot. Try to set up a table, try to find out which ones are which ones should be irrepresentable because they represent something that is invalid, and try to eliminate those by creating a state machine for it instead. And we found out that writing tests for core functions is easy, writing tests for the shell is unnecessary, as I said. And we also found out, well, we didn't find out, we just used our intuition on the idea that untestable code is incomprehensible code. And the entire reason we have bugs in our code is because we don't understand the thing that we've made. So here's a preview into the code quality part for later. What we've been doing are kind of our guiding star. We've been limiting what data is expressible. That's what the state machine did. We've been limiting access to internals. That's why we use channels instead of object references. We've been limiting the possibility of interactions, right? So we're isolating what the kinetic part of our program, what it actually does from what it could be doing. So we're trying to limit the possible interactions to the only ones that are actually real. We've been limiting areas of responsibility so that we divide the program into unique sets of responsibilities so we can focus our attention on one thing at a time and make sure that it's right. Are we seeing a pattern here? What does limiting do? Well, limiting removes the potential. It removes the things that could happen in our code and leaves only behind the things that are actually happening. Once we have only the things that are actually happening in our code, then it's easy to understand. Because our brain doesn't have its attention drawn to all the things that could be happening. It sees, oh, this is what is happening, and therefore I understand what is going on. If we are able to do this, and this has been our guiding star for all of the thinking today, might not have realized it until now. What are we doing? We're untangling what the program does from what it could be doing. We're removing all of the potential and we're leaving only behind the kinetics. This is the preview for the code quality parts, coming in like 1 or 2 weeks. Depends on my form. All right? Limits and untangling. Those are keywords. So I'm going to leave it there for the preview for later. And we are done for today.